Good morning, everyone. Can you hear me and see my screen?
Morning. We can hear you well and see your screen as well. So
Good. Maybe just like last time, I'll briefly put the microphone and video connection on. I'm not sure if you can see, I'm at the campus at the moment. That's a quite nice view from this office where I'm standing at this moment. I don't have this kind of luxury in my home. There's still some people coming in. It's a morning session, so few people are still coming. Let's take them in. Okay. So for today, at first, we'll continue with the same topic as last time. So last time we did a calculation task for a M12 8.8 joint, screw joint, according to VDI 2230. And we learned something how to perform the calculation for calculating the preloading force, allowed preloading force using utilization factor 0.9. And then we learned how to calculate the respective tightening torque. And now the second task would be to calculate M16 10.9 screw. And now we are going vice versa compared to last week. So now the task would be to check what is the achieved preload with a certain tightening torque. So now you need to apply a tightening torque from this table, and you will need to calculate what kind of preload force you will obtain in this bolt, considering that is M.9 screw, M16, and it has been the thread and the nut and the bolt head have been treated with Molykote 7405, which means that it's lubricated to minimize the friction in these contact surfaces. So first, calculate the maximum preloading force with the table torque. You don't need the utilization factor at this point. And then using the stress area of the bolt, calculate the preload stress. And then you would need to calculate this sigma m Joule allowed stress for the bolt as well, using the same equation as last time, and compare the stress that you calculate with the given torque, with the resulting preload force, to the allowed preload stress. And then you can make some judgments out of it.
Excuse me, I have a question, but about the task number 1.
Okay, go ahead.
Yes, it was, yes, first of all, I want to know how many, I mean, the values of the heads, when the heads and the bolts and nut are dry, not oiled, where you can find these values?
You can find them in the lecture material, in the tables.
In the tables, okay. And about the torque, how do you know which torque you have to use?
That is something you need to calculate.
And how do you have to calculate this?
Same answer as last time. Check the lecture material.
Okay. Thank you.
So for this, now we are using some time, maybe half an hour for this task 2, and then we'll move forward. We will start a new topic. We will go into the bearings. We need to start that today so that we have enough time to cover everything we need. And also, if you have questions about the project work, we can deal with those. But now at first, let's finalize this task number 2. And while doing the calculation, keep in mind that some of these designations between the ISO 965 and VDI are not completely uniform. So this minimum core diameter it's a slightly different designation in the VDI and also the stress area. And also the same applies for these inner diameter of the nut bearing area, DA. So in the ISO, it's slightly different. And if you use the similar values as you should be getting around 198.5 kilonewtons of the preloading force.
So I might missed it, but to calculate the force, do we use utilization factor or do we not?
You don't need that in calculation of the preloading force, but you will need this utilization factor when you calculate the allowed stress, and you need to compare the stress in the bolt to the allowed stress.
Okay, but then can I have a hint on how to calculate the preload force? Because I struggle to figure it out now.
So you would be using equation shown in here.
Okay, yeah, now I see.
But of course, it's not given right away in the preload force, but you had to find it.
Great, thank you.
Em nói rồi, hôm anh qua xét á, anh mua con mèo con đi. Anh cứ sợ con mèo con nhức mặt con này nè, nó được cưng nhiều quá rồi nó
So did you achieve a result for this preload force and the stress?
Almost. I still lack some values from the table, and then I'm checking them out.
Okay. When you find, please share them, and especially when you have calculated resulting preload stress and the allowed preloading stress. So please share your ideas and your conclusions out of it.
Well,
Could
I
you please?
calculated the max allowed preload stress, and I got like 750 megapascals.
Just a second. 750 for the max allowed. It was
749.7.
that's quite close in the range I got. I got 764.5.
Okay.
Slight difference, maybe.
I think it's because of the friction coefficient.
Yeah. What did you use as a new G minimum?
0.09.
Okay, that makes the difference. I used as low as 0.07 in the thread and 0.05 in the with the bolt head.
Okay, I just took the middle point. But from there, I have no idea how I used the torque from the table.
But that it's as I think it was was it Nikolai who asked that, but nevertheless, when you check this, where is it? This one, this equation here. Can you see the screen?
Yes.
When you check this equation, you have there. This is in the form that you calculate the torque when you need to have some preload force.
Yeah, I was thinking about that, but I'm actually using the MathCAD Express, so I can't solve any equations.
Yeah, but you don't.
I need to do it manually.
That's a good question, but nevertheless, it's quite easy from here to take the force out of it here. So you just formulate this equation into form that you get the result for F, and in this case, it wouldn't be FM Joule, which stands for allowed preload force, but now we have some torque and resulting preloading force FM, but it's not the allowed because it's not in the limit, or at least should be. But you can see in the results how it goes.
Okay, thanks.
Thomas, do we take pitch dimensions from the ISO table? Is it correct?
Yes, you have to use these ISO tables because mostly they are being given, but you just need to see that the designation differ in these two instances. So this DA and D3, DO, they are not the same in the ISO and VDI equations. So in here you can see that when the VDI equation requires D0, you will use the D3 out of the ISO.
So for the force equation, do we use ISO variables, so to say?
You need to take the dimensions from the ISO tables, but of course this equation I showed you, this one, this is from the VDI.
Oh, Okay.
But nevertheless there are tables which give you all the needed parameters though. So there are tables which give you DKM, but just take into account that in the task assignment I was giving that instead of using nominal DKM, use this equation for DKM. So it's the minimum value for DKM, which is basically 0.97 times the nominal DKM. And the reason for that is that then we can get the
maximum torque or maximum
yes,
force.
exactly the maximum force, and then we can see what is the realized maximum preloading force due to the torque.
Okay, great. Thank you. Thank you.
Okay, now I got the result that preload stress. It's over 1,000 megapascals. Can
Yep.
it be right? Okay.
It can be right, and it is going to be. Did you get something like 1378?
I got like 1,061 megapascals.
Okay, and what was your preload force? It was
Max preload force with the given torque was 152 kilonewtons.
okay. That's probably due to the frictions. It's a little bit less. That I got even more preload force, and then my preload stress is above 1,300 megapascals. And now you can maybe already make a judgment out of the result.
Yes.
But still perform the calculation for the allowed preload stress for this this type of the bolt using this sigma m-Joule equation, and then you can compare the allowed and this resulting preload stress.
Tom, I still struggle to find the D2 and the DKM values because there is only ISO table where I can find D2, and I'm not sure whether it's the one I should use or something different.
Yeah, it's others are the same. So only this only these D3, only these three parameters, minimum core diameter and the stress area and this DA are differing, but otherwise they are the same. So you can use the ISO table for D2, sure.
Okay, thanks. Yeah, one last question regarding the dimensions. So when I'm trying to find the DKI, and I can't see anything from the tables, is it that I mentioned I should calculate myself using 4 more dimensions, or?
I was speaking and the mic muted. Okay, so as you can see, the DKI is the in here. It's the maximum value of those values: DA, DHA, DH, and small da. But in this case, you can use minimum. So it means that this if you calculate the DKM with this well, it's actually it doesn't much matter if you calculate with it maximum or minimum, but then you apply this 0.97 factor in this DKM to obtain the DKM min. So you can use this maximum value as well, but if you want to make it exactly precise, you could use minimum value of these in the equation, because now we are trying to get the minimum diameters to achieve the maximum preload, and therefore the minimum diameters for this contact surface would apply.
Okay, thank you. This is quite clear, I guess. Well, I get quite high preload force, around 250 kilonewtons. Not sure if it's correct.
So you got 252 kilonewtons, or?
Well, basically it's 249, but I just rounded up.
That's quite a lot, sounds to me.
Yeah.
So that was even more that I got. What was your capital P value?
0.2 millimeters. Oh, this is very small.
0.2.
Yeah, I don't know how I got this. Let me check the table.
It should, because that's the pitch of the thread. It should be more.
Yeah, I just realized it. Yeah. So,
in this table, if you see the screen,
it's 2.0. It's not 0.2. That's the problem.
Let's see how it changes.
198. Still.
Yes, that sounds reasonable. I got also 198.5 kilonewtons.
Great.
That is the value for the preload. I will put the other values to the MUR as well. Unfortunately, now we cannot take more time on the calculation itself, so you had to do it finalize it by your own. But the those who did finalize the calculation, you probably found out that the preloading stress due to this torque, it is way above 1000 megapascals. And if you calculate, and when you calculate the maximum allowed preload stress using this sigma m-Joule equation, in this task, this value would be something like 765 megapascals. So we are nearly twice above the allowed stress in the realized stress in the bolt. And now we just used the table value for the torque. So we have table value for the tightening torque, and still we are eventually basically breaking the bolt already in the tightening. And the reason is that because we have this Molykote lubricant, and it doesn't mean that it would be wrong to use the Molykote. It is in some cases it's absolutely necessary to use it, but it's just to give you the idea that how big the effect the friction has on the preload. It has huge effect. So if we would have used normal frictions, we would have probably been in the safe side on the stress, and it would be okay. This is quite good table for general tightening torques. But if you include anti-friction agent in the thread and the bolt area so that you minimize the frictions, even with the table torques, you would eventually break the bolt. And of course, the same applies into another direction. So if you do not apply any lubricant and you are using smaller torque value, you wouldn't get as much preload as you would probably want. So it is really important in the bolt joint where you have to control the preloading, that you control the friction, because that has huge effect on the realized preloading in the structure. So that was the meaning of this exercise. And if there's a variation in the components between these surfaces on the friction, that will also give variation in the preloading force, and therefore it's actually very difficult in the final applications to make sure that you have achieved the needed preload, but you haven't exceeded the allowed stress. It is sometimes quite tricky.
So the way we can control friction is to oil the screw or bolt somehow, or just coat it?
Well, oiling is one option, and but also in there, if you want to be really sure, you will need to do tests with that particular bolt type, with that particular washer type, with that particular oil type that you are using, and still there might be some variation, because there is always variation between the manufacturer components on the frictions. So therefore, this bolt preload control through torque tightening it's quite, I would say, unsure method of the preload control. And therefore, as we last time, I think we checked the video how to use this tension tool, where we can just pull the screw and obtain the final preloading force. That is by far much more accurate method of obtaining a preloading force. But of course, it's quite, I would say, slow and toilsome way of using it. If you have, for example, 150 bolts with a small size, it's quite impossible task to tighten them with this kind of tensioning tool. It should be so. Mostly people use these tightening tools just because it's much more quick, and it's just, reasonably and I would say that sufficiently accurate in cases, but it's not that accurate that you can always rely on it. Okay, so this was about the bolt joints, and as I mentioned last time, there will be some sort of VDI calculation in the exam. I don't know yet which kind of, but some of these types of task 1, task 2 calculation will be. So now when you have this calculation templates ready, then you have good material for the exam. But then we need to move forward or go on to the next topic, which will be bearings. And I think that we can take some slides of this topic today, not all of it, so that we still have time for your questions about the project work. So let's cover it as long as we can. Can you see the screen now?
Yep, we can.
Good. So for today, the learning target would be to recognize different types of rolling bearings, which are sometimes called anti-friction bearings, recognize types of sliding bearings and magnetic bearings. And you would understand the selection process, factors, possible pros and cons of different bearings and their applications. A bearing is a support element of a moving component. And the moving component could be either rotational or axial movement. But the prime idea behind the bearing is it's intended for carrying radial and or axial load. So that could be either axial or radial load, or a combination of the radial and axial loads. Bearings can be categorized according to method of operation. So we can categorize them between sliding bearings and rolling bearings. And the difference between these two being that in a sliding bearing, we have a sliding contact between the moving part and the stationary part. Whereas in rolling bearing, there is a rolling moving element between the rotating part and the stationary part. Another possible way of categorizing bearings is to consider the primary load carrying direction. So sometimes in certain bearing types, it's normal to speak about axial bearings or radial bearings. And those refer to the prime load bearing direction. So our bearing might be a radial bearing, like this sleeve over here, which carries load in the radial direction, but this bearing does not carry load in the axial direction. Or we could have a bearing that is both axial and radial, like this deep groove ball bearing in the picture, which is able to carry both radial load and axial load. Or in some cases, there could be a bearing that is designed only for axial loads and not for radial loads. If we go and look deeper about this division between sliding bearing and rolling bearing, sliding bearing is the oldest type of bearing type. You can see them in cartwheels, like in this picture. They are sometimes called also as sleeve bearings, plain bearings, journal bearings. Numerous designation for a sliding bearing, slightly depending on the application. So the naming is somewhat related to the application they've been using in. There's a good video about the sliding bearings in general, so it takes some while. I think it's 20 minutes, so we don't look it here, but you can check that by your own. But nevertheless, the idea in the sliding bearing is that the rotating shaft is sliding against the static bearing halves. Usually there are half circumference components that are producing the static side of the bearing. And the bearing shell is, in most cases, it's softer than the shaft. And the idea behind is that the bearing would wear before the shaft, because replacing the shaft, if it's worn, would be usually more toilsome, more difficult, and more expensive. But if the bearing shell components are worn, they can be replaced. And one characteristic what is related to the sliding bearing is that they usually only have radial or axial capacity within one bearing element. Okay, another thing is that you will find bearing sets that can carry sliding bearing sets that can carry both radial and axial load, but usually that is done in a way that these elements, they have both radial and axial bearing element for this load carrying function. So as you can understand, if we have a sleeve like this, it will only carry radial load, and if we want to introduce axial load carrying function, we have to perform the sliding surface in axial plane, and therefore they are needed in they need separate bearing elements if we want to have that from the same bearing. The other type, the rolling bearing, is sometimes called so-called anti-friction bearing. And the reason behind is that usually rolling bearings, they have smaller rotational friction comparing to the sliding bearing, at least comparing to this kind of old type of sliding bearing, which has basically no hydrodynamic function in the bearing itself. The difference between rolling bearing and this kind of hydrodynamic bearing is not that big, but nevertheless there is more friction generally produced in the sliding bearing operation. And as mentioned, it means that we have mechanical rolling elements between rotating parts, and a good example is a normal ball bearing, as we can see in the figure here. Some of the bearing types, like the normal ball bearing, they can carry load in both axial and radial directions, but in those cases, usually the other direction, either axial or radial, is larger. So they are usually designed in a way that the primary load carrying direction is either radial or axial. But there are bearings that can carry the same amount of load in both directions as well, like tapered roller bearings, for example. And the basic, most simple component of sliding bearings is to have a sliding bearing without any lubricant. And example of that could be, for example, here in this picture. So we have a soft plastic sleeve between the static and the rotating part, and due to the material characteristics of the white plastic over here, it will provide a somewhat smaller friction than the normal static and rotating part would provide. So usually the bearing sleeve is done out of some low friction material like bronze. It could be plastics and it could be graphite. But of course, everyone understands that the friction in this kind of component is not that low. And therefore it's only for fairly low speeds, fairly low loads, and also it's quite bad against vibration. So these will wear quite fast. But the good side is that you can find components with the material pairs that are suitable for very high temperatures, for the temperatures that you would not be able to use, for example, rolling element bearings, anti-friction bearings. Also, a good side is that because there is no lubrication, okay, the friction is higher, but there's also no contamination from the oil, so it's very clean. And therefore, this kind of bushing bearings are being used, for example, in the food industry, where there is required that you cannot have any oil that could be in contact with the food. They are fairly maintenance-free, of course, given the considered exchange or wear period. When they wear out, of course, you need to replace it, but you don't need to introduce any additional lubrication in between if it's considered that this wear is in designed interval. They are usually quite small, low weight, and the space requirement is fairly small. And because they are not that complex, they are quite cheap components, simple, and you can find in various sizes. One example of using this kind of simple bearings is a joint of a mechanism. So if you have pin joint or a hinge, for example, in some sort of packaging machine mechanism, usually the bearings in the pins are this kind of quite simple bearings because the loads are not that big and it doesn't rotate that fast. So it just needs to provide the ability of the pin to rotate.
Excuse me.
Yes.
Can you speak again? Like why does the roller things cannot be like work in high temperature?
If you are using a normal rolling bearing like this, it will always require some lubrication. And if you have a lubrication, meaning usually oil or grease introduced in the temperatures like 1000 degrees, 1500 degrees, it will burn.
Yes. Thank you.
Okay, then next, a little bit more advanced version of sliding bearing is self-lubricated sliding bearings. So it's not that much different from the previous one, just that there is being introduced some kind of lubricant, which is impregnated to the structure of the bearing. So usually it's grease, it could be oil, it could be graphite. And usually it's done in a way that the bearing material contains micropores, like in this, I don't know if it's bronze or copper, but you can see that there are small holes in the material. And in this right-hand side picture, there are even bigger holes. But these holes can contain the lubricant and therefore provide lower friction comparing to the non-lubricated sliding bearings. And therefore, the materials that we use are usually so that they contain naturally some pores where the lubricant can be stored into, like cast iron and other metals that can have porous structure. And of course, these bearings, when they introduce lubrication, they can provide higher load and higher speed capability compared to these simple bearing types. But nevertheless, also these are not that good in vibrating conditions because the lubrication film, it's not fully consistent and it will easily go away from the contact point due to the vibration. So also these will wear quite fast if they are in vibrating conditions. Well, if the fast is too fast, depends of course on your application. So if you have an application where you can maintain or exchange these components every 6 months, then the fast wear probably wouldn't be a problem. But nevertheless, it's something you need to consider while selecting the bearing. Then the third, yeah, please go ahead.
Yeah, I had a question about sliding bearing. Recently, we had an assignment in another course with Simo Cinco, and we were doing well, we were assembling a rotary feeder, and for the shafts, we put sealing unit on the shafts, and between them there was an element called in Finnish kulutusholki, as far as I remember. Is it a sliding bearing or what is it? Because
Kulutusholkki, was that the word?
yeah.
Okay, then it's the kulutusholkki stands for a wear out sleeve. If when I don't know what is the application, I can't say if it's performing the function of a sliding bearing or not. It could be just for the reason of providing a surface, for example, for the seal to touch, so that if the seal is over time, it's making groove onto the surface, it would make the groove into this kulutusholkki and not to the shaft itself. The primary question is that does the load come through this kulutusholkki? If it does, then it's basically a sliding bearing. But if the sliding bearing is there only, for example, between the seal and the shaft, then I would say it's not a sliding bearing.
It's hard to say whether there is a load, but I suppose there is. So okay, I may assume that it's a bearing. Thank you.
Yeah. Then you may assume that it's sort of a bearing. So in the most simple manner, as you mentioned, it's this sliding bearing could only be a sleeve, just a sleeve, and that's performing the bearing function to carry the load. So the idea so that it makes the bearing is that it will carry the load. So I know that there are some sleeves which are being used purely for the intention to protect the shaft surface from being scratched due to the touching of the lip seal, for example. So that would not be a bearing. A bearing is always a component that is intended for carrying the load.
Yeah, so when there is a support function, it means that it is a bearing.
Yes.
Yeah, right. Thank you all.
Okay, then a bit more advanced version of sliding bearing is a fluid film sliding bearing. And as the name says, we have a shaft which is rotating on a fluid film, which is between the static and the rotating part. And this is one step more advanced version, so it will eventually have smaller friction comparing to these previous self-lubricated and non-lubricated sliding bearings. And in this fluid film bearings, we have two main types. One of them is hydrodynamic bearing, and the other is hydrostatic bearing. Both do contain the word hydro, which somehow gives the idea what is the basic idea behind the functioning. First of all, the hydrodynamic bearing. And the idea in the hydrodynamic bearing is that the shaft is sliding on a fluid film. And when the shaft is sliding, like if we look at this right-hand side picture, while the shaft is sliding fast enough, it will create so-called hydrodynamic lift. And as a result, the shaft is basically levitating from the static part of the bearing. So there is oil film between the shaft and the static part, and due to the velocity in this tangential velocity in this contact area, the shaft doesn't touch the static part at all. So there's no contact between the shaft and the bearing. Of course, there is a contact when you start it. When it's when it's not running, your shaft is of course touching the bearing. But when you have speeded up into sufficient speed, then the shaft will rise onto the fluid film. And usually these bearings are done from fairly soft, low friction white metal, or so-called Babbitt metal. And Babbitt is an alloy of tin, copper, and antimony. And the idea is that they are soft, so that they would wear before the shaft wears. And also another point is that they have inherently low friction, so that they will provide the low friction to the starting seconds of the machine, so that it wouldn't wear too much while starting the machine. Of course, when it's up and running in full speed, then there is no touching at all anymore. And this hydrodynamic bearing, due to this lift and non-touching function, of course, will provide higher speed and load capabilities comparing to the previous versions of sliding bearings. So therefore, there is only viscose friction. So viscose friction is coming from the viscosity of the lubricant. There is no friction from the contact of the shaft to the static part at all. And therefore, the friction is related to the lubricant and what is the viscosity of the lubricant. The higher the viscosity of the lubricant, the higher is the load capacity, but also higher friction due to the rotation. Jaakko, you have some trouble hearing, probably. Okay, it must be your connection. I didn't see any sign of poor network connection in this side. There could be sometimes. Let's continue. And also what is good side in this hydrodynamic bearing is that they provide fairly good damping. And the damping is due to that there is a thickness of oil between the component. That is, you could imagine it as a sort of cushion that is or pillow that is providing the free movement and from there providing the damping properties for this kind of bearing. And another good side is that because there is no touch between the component, it's basically providing infinite lifetime if you have a continuous running operations. With the proper application, there's never touching between the rotating part and the static part, and it will never wear out. When I was working in an engineering company, we had one case in which they had we need to renovate a pump house which was built beside the Lake Saimaa here in Lappeenranta, and the pump house had been built I think 1910 or something like that, really old. And there was a propeller shaft that was rotating really slowly, so that it didn't pump that much, but it only increased the water level by 10 centimeters or something like that, very low, and therefore the rotational speed was very low. And there were sliding bearings which were in the lake. So the shaft was put, of course, in the lake, and the bearings were made of wood. They were wood bearings, and they had lasted nearly 100 years of this operation in this water. But it was running 24/7, only some short maintenance breaks every now and then. So we were really surprised when we found out that okay, there had been wood bearings and they had lasted for nearly 100 years in the operation. So if you have a good conditions for this kind of hydrodynamic bearing, they will last forever. Well, comparing to previous designs, there is also some downsides, and one of them is that it will require the lubricant, and it will require the reservoir, meaning the storage for the lubricant. Usually the cavity of the shaft and the bearing itself, it is not enough. So you need to have some additional container somewhere nearby where the oil can flow and maybe a little bit cool down by itself. So just filling the bearing and the shaft intermediate space, it's not enough. And also because this speed is creating the friction, if you increase the speed a lot, it will increase the friction quite a lot, and therefore the temperature will increase in the oil. And therefore, if you're running higher speeds, it will require oil cooling, which then requires a separate unit for cooling the oil, and also a circulating pump to circulate the oil from the bearing to the cooling unit. And of course, also the basic function is dependent on the tangential speed on the shaft surface, which means that you need to have sufficient speed. If the speed is too small, there will be metal-to-metal contact and there will be rapid wear. And therefore, it's not very good in the application where you have a high number of repeated starts and stops, because then you will have many times this touching between the components before it's finding the hydrodynamic operation state. These bearings are extensively used, like in electric, steadily running electric motors and generators, also in vibrating conditions due to the vibration function of the oil film. And also of this, I would recommend check this video, which is in the link. That's quite good explanation about the hydrodynamic bearings. And it is also providing information about tilting pads, which is special design of hydrodynamic bearing, just that the bearing is formulated in different sections which can independently align themselves. One of the downsides of this basic function of hydrodynamic bearing is that you will need to have quite precise form of the cavity between the shaft and the bearing. And if the shaft is deflecting, that will sometimes cause friction and wear in the certain point. So this area between the shaft and the bearing should be as cylindrical as possible. And there's a solution to that which corrects this sort of anomaly, and that is tilting pads. Then going to even more advanced bearings, we have a hydrostatic bearing. And like in the previous one, we had the shaft motion that created the lift for the bearing. Now we don't need the shaft motion to create the lift, but we are producing the lift onto the shaft by a pump. So in this form of bearing, the shaft is sliding on a pressurized fluid or gas. It could be also gas. And this pressurized film has to be created by a pump. One example of this is a car crankshaft, where you have these oil holes which are going through the crankshaft, and they are going to the connecting rod bearings. And this is a form of hydrostatic sliding bearings. So the oil pump of the car is producing oil pressure, and the oil is pressed through the small clearance between this crankshaft bearing and the connecting rod, and therefore creating this levitation for the connecting rod in the operation. And this kind of bearing design, it has excellent damping properties. So therefore, it's suitable also for very highly vibrating applications like combustion engines. And if it's required to have very low, near zero friction, which usually it's not possible with the liquid. So if you use oil in this kind of application, this viscosity of the liquid will create always some heat, some friction. But if we require nearly zero friction, air can be used as a supporting medium. So there's a pump that is pumping sufficiently amount of air into the bearing, and the shaft is levitating on the air pillow. That's called foiled air bearing. But the downside of foiled air is that it requires very high precision from the components, and it's quite complex and expensive. And from that reason, it's only used in quite special applications like in jet engines. Another problem is also that if the pump for some reason fails, so that you really release the air pressure, then you will basically destroy the machine, because it will rapidly wear the components if they are touching each other. The good side of this bearing type, the hydrostatic bearing, is that you can achieve low, basically zero speeds, because you don't need the motion of the shaft to create the lift. So you can just use the oil pump to lift the shaft up and levitate the shaft, and the shaft doesn't need to rotate for that. And like the previous one, the hydrodynamic bearing, also hydrostatic bearing, they have basically, they provide the infinite lifetime for the bearing components if there's a proper lubrication and there's nowhere due to any reason in the operation. But of course, again, it requires a pump, and the pump has to be fairly high capacity pump, so that it is able to produce the high pressure, and it requires that the system is a bit more complex, and it's a bit more expensive. But they are being used, for example, in compressors, turbochargers, high-speed motors. By the way, turbocharger bearings are this kind of bearings as well. So the oil is fed into the clearance between the turbocharger shaft and the bearing outside shell. One application of hydrostatic bearing is, for example, a type of electric machines that been used in ships, in vessels that do operate in intermittent intervals. So when they need to drive back and forth, the motor might be starting several times within a minute, and the direction might be changing. So in those applications, they use hydrostatic bearing to prevent the wear out. Okay, that was the sliding bearings. Then for the rolling bearings. So on the contrary to the sliding bearings, in rolling bearings, we have a mechanical element between the rotating and static part. Like sliding bearings, there was no mechanical element, but here we have a component that is providing the movement in the interface. Usually they are balls or cylindrical barrel-shaped or tapered rollers. There could be some also needles when it's called a needle bearing, but that is, I would say, a form of cylindrical roller bearing. Just that the diameter of the rolls is very small. Rolling element materials are usually, they are steel, but it could be also ceramic. Then they are called so-called hybrid bearings. And in hybrid bearings, I would say that in most cases, the rolling elements are ceramic, but there are also very special bearings in which the raceway is made of ceramic material. In this picture, you can see a basic configuration of a rolling bearing. So we have an outer raceway, which is usually the static part. Usually the shaft is spinning, but it could be also vice versa. It could be that the shaft is static and the outer side is rotating. Then we have the rolling elements. In this case, they are the balls. And we have a cage, which is the component which is keeping the rolling elements at intervals from each other and keeping them then in place and preventing them from touching each other. Then we have the inner raceway, and in some types of the bearings, there could be also a seal that is either there for keeping the lubricant inside the bearing or keeping the contamination, particles, dirt outside the bearing, or both. The lubrication, which is always needed in rolling bearings, can be provided by self-lubrication, which means that the bearing is so-called greased for life bearing. So there is, in the manufacturing, there's been put some amount of grease inside, and then there are the seals which contain the grease inside the bearing during the operation, and the grease is designed to last certain hours, and in many applications that is quite sufficient. So you don't need any additional lubrication to the operation. Most of the small size bearings are this kind of bearings that are grease for life. Then there could be oil lubrication, especially in the cases where you need to somehow also get rid of the heat due to the contact. So in those cases, oil lubrication is being used, and also with very high speeds where grease is not anymore an option. And the grease lubrication can also be introduced with the periodic regreasing. So there could be a pipeline to the bearing, and there could be a greasing device that is pumping grease to the bearing at certain intervals. Quite common procedure in industrial application is that there is a so-called centralized greasing system and grease pipes to each of the bearing, and they feed each bearing depending on the speed and load capability, load requirements for individual bearings. Also for this, you can check the video about the rolling bearings by your own. And compared to the sliding bearings, the main benefit is that with rolling bearings, you have very low friction. And therefore, as mentioned, they are sometimes called anti-friction bearings. Materials are usually specific, very high alloys, hardenable bearing steels, and they have a yield strength up to 2000 megapascals and even above. Very hard steels. Cages, which are the components that are keeping the rolling elements from touching each other, they are usually manufactured from steel, aluminum, plastics, or brass. And the speed that you can apply with the rolling bearing, it's depending on the bearing size, and the crucial factor is the tangential speed of the rolling element. So basically a combination of the bearing size and the rotational speed is the tangential speed. Speed is dependent on the construction type. There's also seemingly a word of Finnish also included. So speed depends on the cage. What is the material of the cage? The cage could be plastic, which doesn't then allow very high speeds, of course. The cage could be brass, and the cage could be steel. Speed is also dependent on the rolling element mass and eventually meaning the rolling element material. Hybrid bearings, for which these rolling elements are out of ceramic material, they usually provide higher speeds because the ceramic material is of lesser weight compared to steel. Lubrication is affecting onto the limiting speed, and usually these bearing systems are designed in a way that there are certain bearings which are axially fixed and others that are axially floating bearings. If you, for example, look at the bearings over here, there are two bearings, and typically either of them is a bearing that can freely move in the axial direction. Here is a better picture out of it. And the reason is that in many applications you have thermal expansion affecting and therefore you need to allow the thermal expansion to happen in some location, and that is done by allowing another bearing to move freely. And then it means that this bearing which is not moving freely, it's providing the axial load carrying function. This is something that you have in your project work as well. So the other bearing, I think it was the in your application, it was the gearbox side, the right-hand side bearing, which was defined as a locating bearing. That's the one that is carrying the axial load. And in your case, the hub side bearing is now the floating bearing that can freely move in axial direction, and it means that it cannot carry the axial load. Sometimes these floating bearings can be spring-loaded, especially in vibration conditions, and in some cases due to the reason that bearing needs to have a certain minimum load. So if there's a risk of too little load for the bearing, there are also springs added, which create sort of artificial load to the bearing and enable the normal operation for it. These locating bearings, when we need to use them, they are usually with a tight fit on the shaft. So there's an interference fit between the inner raceway and the shaft. And in addition, they are usually also secured, for example, with a shaft nut or a retaining ring at least. Bearing calculation, that we will look further and in more detail next time. It will be according to ISO 281 or ISO 16281. And both European major bearing manufacturers, which will be FAG Schaeffler and from Germany and SKF from Sweden, they provide this kind of online calculation tools which we can use for designing and calculation your bearing setups. Next time we are going to look this SKF calculator a bit and make a simple calculation with it. Okay, but now I think that so that we would have at least some time for the project work questions, we'll stop this topic now and continue next time. So if you have any problems or questions related to your project work, we can take them now.
Yes, I have some minor problem in my project.
Okay, would you like to say it here so that everybody can hear and maybe also share the information?
Yes. When
Or do you want to have a breakout room?
I think it's okay when I share here. When I choose the diameter for the smaller shaft, the static safety factor is like 1.9, and when I calculate the fatigue safety factor, it's just like 1.05, 1.04, and I don't know if it is good choice for my diameter or not, because like I see that the safety factor for static load is like quite okay, but like for the fatigue safety factor is something like too small. Am I right?
Yeah, that is possible that it could happen, because I haven't beforehand. I haven't calculated the cases of each of you. So there could be some combination of the input values that provide this kind of situation that you can't meet the all of the requirements. But then nevertheless, you are above 1 regarding the fatigue, so I would say that it's okay. I think I didn't define a requirement for fatigue safety factor, but it just needs to be, of course, above 1. And you said that, did you say that the 1.05 was the safety for against fatigue?
Yes.
Yeah, then I think that it's nevertheless okay. It's still over 1, and against static you have fulfilled the requirement to be between 1.4 to 2. But if you would like, you could maybe try also that if you could, for example, increase the radius between the D1 and D2, or do some other modification, maybe increase the diameter so that you would be exactly on 2 safety factor in the static. How much would it help your fatigue case?
So that doesn't mean like I should increase the diameter of larger shaft, isn't it?
I think if you increase the D2, I think it will not help you, because then you will basically increase the notch effect. So I think you should either increase D1 or increase the radius between the D1 and D2.
If I increase D1 is like over safety factor of 2, so it is not meet the requirement for the task, isn't it?
Well, can you select the D1 so that you would be exactly on 2 on the static analysis?
I would say like I don't know, because like when I have mentioned with you with the bearing things. Do you remember that?
Okay, I remember now. You were the one who checked the bearing radius also. Yes, I understand that. Okay, yeah, you got a point in there. In this, then I think that it's yeah, you can use this 1.05. It's still above 1, so it's okay. Just that given that the calculation is done correctly.
Yes, thank you.
Okay, you're welcome. So as others also heard, Min had checked also what is the possibility for the bearings to be installed. So if the radius between the D1 and D2 is far too big, then you don't find any bearing that would anymore match this geometry. So the bearing would hit the radius and not meet the bearing journal. Okay, anyone else?
Yes, can I choose some questions in a private room, because it's about my units and, well, some units in my calculations, so maybe it's better.
Okay, so you want to take a breakout room?
Oh yeah.
Okay, let's do that. Just a second.